Welcome back to another video. I'm David, and in this one we're going to be discussing one of the most important examples of cycloadditions in organic chemistry, the Diels-Alder reaction. Let's get right into it. The cycloaddition of alkenes and dienes is a very useful method for forming substituted cyclohexenes. So, when discussing Diels-Alder, in this case, this is the diene and this is the alkene. We refer to the alkene as a dienophile. Cycloaddition reactions result in the formation of a new ring. In this case, we form 6-membered rings, cyclohexenes, and this formation is a result of a concerted mechanism, which requires that a single transition state and therefore no intermediate lie on the reaction path between reactants and adduct, or product. This is the transition state of this paracyclic reaction, in which it takes place in a single step by a cyclic redistribution of bonding electrons. The two reactants, the dienophile and the diene, join together through a cyclic transition state in which the new carbon-carbon bond forms at the same exact time. Now, this is a more detailed description using molecular orbitals to show the concerted mechanism. It's a single transition state, it's paracyclic, meaning it's a cyclic redistribution of bonding electrons. So what we see here, and when we get to practice problems, is that the alkene or dienophile moves its bonding electrons there, this pi bond moves here, and this pi bond moves here. We like to use the red dashed arrows to show the formation of the new bonds for simplicity's sake. In this Diels-Alder transition state, the two alkene carbons and carbons 1 and 4 of the diene rehybridize from sp2 to sp3 to form new single bonds. Now there's two new single bonds that are forming, while carbons 2 and 3 of the diene remain sp2 hybridized to form the new double bond in the cyclohexene product. The new double bond in the cyclohexene product is seen here. Now, before we get into practice problems, it's important to take some notes on the characteristics of the Diels-Alder reaction. In this part, we'll look at the dienophile, and in a couple minutes, we'll look at the diene. Overall, the Diels-Alder cycloaddition occurs most rapidly if the alkene component, the dienophile, has some electron withdrawing groups. As we'll see with substituent effects in a nearby video, for electrophilic aromatic substitution, we will learn that substituents play a serious role in determining the reactivity of some substrate. Electron withdrawing groups withdraw electrons and therefore make the alkene more reactive, whereas electron donating groups donate electron density and make it unreactive or less reactive. In almost all cases of Diels-Alder that we'll be going through, the double or triple bond of the dienophile is going to be adjacent to a positively polarized carbon atom due to an electron withdrawing group that's attached to it. So, let's talk about stereochemistry in regards to the Diels-Alder reaction. It's one of the most useful features of this reaction. It's because it's stereospecific. In other words, the stereochemistry of that dienophile is retained. So, what that means is if we have a cis dienophile, we're going to end up with a cis product. If we have a trans dienophile, we're going to have a trans product. One more stereochemical feature of the Diels-Alder reaction before we get into practice problems is in regards to diene and dienophile. They orient so that the endo product is formed rather than the exo product. These two words are used to indicate relative stereochemistry when referring to bicyclic compounds. So what we mean here is that this group that was added is cis to this or endo to that. If it were anti or exo, it would be facing up, which would mean it'd be away from this. Now taking a look at the diene must adopt an S-cis conformation, cis-like about the single bond. So, this is S-cis, which means carbons 1 and 4 are close enough to react to form a cyclic transition state. On the other hand, this is the S-trans conformation. So, what's going to happen here is a rotation about the single bond to place the two carbons, 1 and 4, in close enough proximity so that they can form that cyclic transition state. So let's take a look at this first practice problem. With all these practice problems, I've already drawn in the red dotted lines. So you're going to want to do that from carbons 1 and 4 of the diene to carbons 2 and 3 of the dienophile. So now we can run the reaction. Perform the cyclic redistribution of bonding electrons. Take note that this can go either way, so we can take this in either direction. So this could have gone this way, and this could have gone this way. But for the sake of this, we'll do it in this direction. So when these bonds are formed from the redistribution, the cyclic redistribution of the bonding electrons, we're going to get several new bonds. We're going to get one right here, we're going to get one right here, and we're going to get one right here. And that's going to be a double bond. And so the final product is going to look like this. So let's draw in the new bonds, the ones that we formed right here, here, and right here. There's your 6-membered ring. That's the adduct. All right, so the next practice problem. Take note, we have a triple bond. Take note, this is S-cis, so we're in a good conformation state. And we have an electron withdrawing group, so we're set to run the reaction. Let's move with cyclic redistribution. We're going to form a cyclohexene. But take note of that triple bond. We'll see what happens in the product. All right, so the new bonds that formed, the double bond, and the sigma bonds between the dienophile and diene, and we have a new 6-membered ring. This pattern is extremely repetitive, so once you run through some practice problems, you're going to start to see this. It's the same thing over and over. You need that electron withdrawing group. You're going to cyclically redistribute the electrons about the molecule to form a 6-membered ring with no reaction intermediate besides, theoretically, the transition state. All right, so let's do this one. We have a carbonyl group, which is an electron withdrawing group, on the dienophile, so we're set there. Double bond, everything looks good. However, the diene is in the S-trans conformation, so we need to do a rotation about that single bond, the sigma bond, to form a compound in which the first and fourth carbons are close enough to form that cyclic transition state with the dienophile. So here's what we have. We move the dienophile double bond. We move these pi electrons cyclically. Stay with the same direction or change. It doesn't really matter. It's whatever is comfortable for you. Here's that new pi bond and the 2 new sigma bonds between the diene and dienophile with our electron withdrawing group. All right, so lastly, this reaction may look a little familiar, but let's run it. We have not yet done a diene that is a cyclic compound. So let's walk through this. Same procedure over and over. Draw your dashed lines from carbons 1 and 4 to carbons 2 and 3 of the dienophile. Cyclically redistribute the electrons. And because we're talking about a cyclic diene, we're going to form a bridged head carbon, and an endo product will be formed. So here's a more accurate representation. We saw this earlier when we were talking about the endo product, and this is, in fact, what we get, the endo product. So let's draw the cyclic redistribution using this more accurate representation. So we move these pi bond electrons here. We move these up here. And we move them right there. So use those dashed lines to help you. Use them to guide you. And here, the endo product forms. New bond here. That's that new pi bond that forms. This bond is new. And this bond is new. If you have any questions, leave them in the comments below or email us. And if you have any feedback, drop that in the comments as well. Thank you for watching. We hope to see you in the next one. I know this is a quick video, but if you want more help with the Diels-Alder, just leave a comment and we can, of course, do some more practice problems. So thank you for watching. We'll see you guys in the next one.